All right, let's dive right in. We're going to talk about going from data to discovery, and really how to make sense of all the numbers that are constantly flying around us. So let me ask you something, and I bet you can relate. Have you ever felt like you're just drowning in information? I mean, it's this constant flood of facts, figures, and stats coming at you from every single direction. Because in today's world, data is literally everywhere. But here's the catch. Raw data, just by itself, is pretty much just noise. It can be messy, chaotic, and it definitely doesn't tell a clear story right out of the box. So that's the big question, right? How do we find the signal in all of that noise? How do we take that chaos and turn it into something clear, something that tells us a story? Well, that's exactly what we're going to break down. Our whole journey from noise to signal, it really starts with this amazing tool from the Python programming language called Pandas. Honestly, the best way to think about Pandas is like a Swiss Army knife for data. It's incredibly versatile, super efficient, and it's pretty much essential for anyone who's trying to get a handle on raw information. And the heart and soul of Pandas is something called a data frame. The easiest way to picture it is like a spreadsheet, but a superpowered one. It has rows and columns, but it's built to handle massive amounts of data with incredible speed and ease. And with a data frame, you can do so much. You can pull in data from pretty much anywhere. We're talking CSVs, Excel files, even big SQL databases. Then you can quickly check it out, clean up all the messy or missing bits, and totally reshape the information to fit whatever you're trying to do. It's that first crucial step in creating order out of chaos. Okay, so once our data is clean and all organized in one place, we can finally start trying to understand its story. And that's where descriptive statistics come into play. Usually, the very first question we ask is, okay, what's the typical value here? Like, if we had to pick just one number to represent the center of all our data, what would that number be? And for that, we've got two main players, the mean and the median. Now, the mean is just your classic average. You add everything up, divide by how many you have. Super simple. But it has a weakness. It can be thrown way off by extreme values, what we call outliers. Think about it. If you have a room full of people and a couple of billionaires walk in, the mean income is going to look ridiculously high. The median, on the other hand, is just the number smack dab in the middle. It's way more robust, so those billionaires wouldn't really affect it. Knowing which one to use is absolutely key to telling an honest story. But just knowing the center isn't enough to get the full picture, not even close. We also have to ask, okay, but how spread out is all this data? Are all the numbers clustered tightly together, or are they all over the map? And that's where standard deviation comes in. It sounds complicated, but it's really just a number that tells us how far, on average, our data points are from the mean. A low number means everything is consistent, all bunched up. A high number means the data is really spread out, and that tells a completely different story. So now that we've kind of described the shape and center of our data, we can move on to the really exciting part, looking for those hidden relationships that are lurking inside. And we do this by looking for correlation. At its core, correlation is just a number that tells us if two different things, two variables, tend to move together in a predictable way. It's really simple. A positive correlation just means that as one thing goes up, the other thing tends to go up too. And a negative correlation, you guessed it, as one thing goes up, the other tends to go down. That's it. But, and this is a huge but, before we get all excited and start finding connections everywhere, we have to talk about the single most important, the golden rule in all of data analysis. Correlation is not causation. Just because two things happen to move together does not mean one is causing the other. I mean, a classic example is that ice cream sales and shark attacks are correlated. They both go up in the summer, but one doesn't cause the other. Remembering this is what separates a good data analyst from someone who draws dangerously wrong conclusions. So this entire journey we've just taken, from wrangling all that messy data to uncovering potential relationships, it actually has a name. It's called Exploratory Data Analysis, or EDA for short. And you can really break this whole data journey down into 5 main steps. First, you load your data to get it all in one place. Then you clean it, because trust me, real-world data is always messy. After that, you describe it using stats to get a feel for it. Next, you start looking for relationships and patterns. And finally, you identify any weird outliers that might be throwing off your results and telling you a false story. Now, a lot of the time, we can't analyze all the data. the population, which is the entire group we're interested in, is just way too big. So what do? We use a sample, a smaller, representative slice of that big group. The whole goal is to use that manageable little sample to make educated guesses, or what we call inferences, about the much, much larger group.
So why do we do all this? What's the point? Well, we follow these steps to build models, to make predictions, and ultimately to uncover these really powerful insights about the world all around us. This is how raw data becomes true discovery.
Which brings me to one last question for you. Now that you know the basic roadmap, this journey from raw noise to real insight, what hidden story that's out there in the world's data would you want to be the one to uncover?